These are the frequently asked questions for Algebra 2 for section 5.3, day 1. Going back and doing some factoring, we're looking at number 11. We have x cubed minus 1,000 equals 0. And this is a difference of two cubes pattern. We have the subtraction in there, and we notice that this is x cubed, and this is 10 cubed. So that's going to be a and b in our formula for factoring the difference of two cubes. And remember, in this formula, because this has subtraction in the original problem, the subtraction is going to show up in those first set of parentheses. So this will be x minus 10, just substituting x in for a, and then 10 in for b. And then we'll have x squared plus 10x plus 100. And we are supposed to solve this, so we're going to keep going. X minus 10 could equal 0, so x equals 10 is a solution. And then with the second one here, generally this does not turn out to be factorable. And I say generally because it's about 90% of the time this piece is not factorable. So we can stop and think about it for a second and try to come up with two numbers that multiply to 100 and add to 10, or check to see if this is a perfect square trinomial, and it's not. But in the end, we're going to have to complete the square or use the quadratic formula. So I'm going to complete the square. I'm going to move that 100 over to the other side, and then take my b value, which is 10, and divide it by 2, and then square it. Well, that's going to be 5 squared, which is 25. So what I add to one side, I have to add to the other. So this will now be a perfect square trinomial. I forced it to be. And what you square to get x squared is x, and what you square to get 25 is 5. And then over here we'll have a negative 75. You continue to solve, take the square root of both sides. So x plus 5 equals plus or minus the square root of negative 75. Well, the square root of negative 75 has to be simplified. So we'll pull out that square root of negative 1 so we can get an I in there. And then 25 goes in 3 times. So x plus 5 equals plus or minus, there's our little I, and there's a 5, and there's the square root of 3. So that looks really awkward. I'm going to go ahead and put that in standard form here. So that will be plus or minus 5 square roots of 3, I, and then I'll go ahead and subtract 5 from both sides. And there it is. So we ended up with one real 0 at 10, and then 2 imaginary zeros for that one. And again, you'd get the same answer if you used completing the square, or I'm sorry, use the quadratic formula for the second one here. So just work carefully as you go through it, and you'll be fine. All right, now I'm going to have to erase that because all of these take quite a bit of work. So going back up to number 13, we have 64x cubed minus 1 equals 0. So things you think about, of course, are, do I have a common monomial factor I can pull out? No, but special patterns, yes. This is, again, going to be the difference of two cubes. So I, again, use that formula a minus b times a squared plus ab plus b squared to figure out those zeros. So this will be 4x minus 1. And then if you take 4x and you square it, the entire quantity, you're going to get 16x squared. A times b will give you 4x, and then 1 squared, of course, is just going to be 1. So the first 0 here, we'll set 4x minus 1 equal to 0, and then we'll add 1 and divide by 4, and we get a nice little 1/4. But then we have this monster. And again, not factorable. So we're either going to complete the square or we're going to use the quadratic formula, and I'm going to go ahead and complete the square. And to complete the square, we have to have a 1 in front of our x squared term. So that means I have to divide everything by 16. That will give me x squared plus 1/4 x plus 1/16 equals 0. I'm going to go ahead now and move that 1/16 over. And you could have done that right away, it wouldn't make any difference. But then I need to complete the square. So I have to take my 1/4, divide it by 2, and then square it. Well, dividing something by 2 is the same thing as multiplying it by 1/2. So that'll be 1/8 squared, which is 1/64. So I need to add 1/64 to both sides. All right, next thing to do is to write the left-hand side as a binomial squared. So you have to think back, what did I square to get 1/64? Oh, I wrote 1/16 here. That's 1/64. That was 1/8. And then over on the right-hand side, we would multiply the top and the bottom of this fraction by 4 to get that into 64ths. So we would have a negative 4/64 plus 1/64, which is a negative 3/64. Then we would take the square root of both sides, and x plus 1/8 would equal plus or minus, and then we're going to start breaking this one down. We're going to take an I out because that's the square root of negative 1, and then we'll have the square root of 3 over 8, and we can always put that I in the back later so it's in standard form, because what we need to do is we need to move that 1/8 over by subtracting. So negative 1/8 plus or minus the square root of 3 over 8I to get that in standard form. So again, not real pleasant. The first one, very nice, real 0 and 1/4, but the other two, taking some work. You only have to figure out where those last zeros would be, because a cubic has a degree 3, and that means we should be able to find all 3 zeros, and that's what we want to do in math. We always want to find everything. Number 17, 0 equals x cubed minus 64. And again, I notice that this is a difference of 2 cubes problem, and get to work on it. So it's the same formula we've seemed to use now for a lot of these. And in this case, this is going to be x minus 4. Again, using x for A and 4 for B. And then we'll have x squared plus 4x plus 16 equals 0. The first 0, really easy to find. That's going to be a 4. This one, you make a decision. I'm going to make a decision to complete the square. Because my first term is just 1x squared, I don't have to do any division. I just need to move the 16 over and complete the square. So b value is 4. 4 divided by 2 squared is going to be 4. So we're going to add a very nice little lovely 4 to both sides here. And this will be x plus 2 squared equals negative 12. You take the square root to both sides, so x plus 2 equals plus or minus. Whenever you write that square root symbol down, remember you have the positive and the negative. And we have an I in there, and then the square root of 4 and the square root of 3. So x plus 2 will equal plus or minus 2I square roots of 3. And then we can go ahead and subtract 2 from both sides and then put the back term in standard form. So plus or minus 2 square roots of 3 and then an I. Remember, complex numbers in standard form are A plus BI. So we always have that I hanging out. So real part of the problem answer is in front, and then the imaginary is in the back. So that was number 17. Get that off of there and go to number 19. Number 19 is 64x cubed equals negative 8. So the first thing we do is bring it over to one side and take a look at it. And then I notice those numbers are looking pretty big there, but 8 goes into both of those. So I factor out the 8, and I'm left with 8x cubed plus 1 equals 0. And now I can keep going because 2x cubed is 8x cubed. And then 1 cubed is a positive 1. But this time, what we see is a sum of 2 cubes. So that formula is going to be a plus b times a squared minus ab plus b squared when we factor that one. So our 8 out in front really isn't doing a whole lot. It's not going to be a source of any zeros because it doesn't have an x, but we're going to bring it along for the ride. And then if we use 2x for a and 1 for b, we will get 2x plus 1, just substituting into the formula. But then 2x, the quantity squared, is going to give you 4x squared. And that would be minus 2x times 1, which is 2x, and then plus 1 squared, which is just 1. So the first 0 that we see here comes from 2x plus 1 equaling 0. We subtract 1 and we divide by 2, and we get negative 1/2. And then for the second one, again, we have a choice. And that choice would be we can either complete the square or do the quadratic formula. I'm going to go ahead and move the 1 over, and then divide by 4, because whenever you complete the square, you need to have a 1 in front of your x term. So we have x squared minus 1/2 x equals negative 1/4. And now I need to take my b value, which is negative 1/2. I need to divide it by 2 and then square it. And again, dividing by 2 is the same thing as multiplying by 1/2. So that will be a negative 1/4 squared, which will be 1/16. So I need to add 1/16 to both sides. And on the left-hand side, I do have a perfect square trinomial. This will be x minus 1/4 squared. And then on the other side, I'm going to have to multiply the top and the bottom of that first fraction by 4 so that I have a common denominator. And that'll give me negative 4/16 plus 1/16, which is a negative 3/16. Square root of both sides. And x minus 1/4 equals plus or minus. We have a negative, so we're going to have I square root of 3 over 4. And again, we can reverse that when we're moving the 1/4 over. So we add 1/4 to both sides and make this the square root of 3 over 4I when we do that. So again, most of the work from this is going to come from the completing the square or quadratic formula process when we get that. But we did find them all. And that's, you know, good achievement. We want to be able to figure out what are all of these. All right, smartboard, there we go. Behaving itself. So that was number 19. And now I want to go after number 23. So I'm going to go ahead and move that 18 back over in the hopes that this is just straight up factorable. And I noticed that I have the x to the 4th, but I'm not too worried. I checked to see if there's a common monomial factor, and there's not. But we don't have a perfect square trinomial either, because we have that negative 18 in the back, and that is not a perfect square. But we certainly know that x squared times x squared is x to the 4th. So then what we need to do is come up with two numbers that multiply to negative 18 and add to 7. And that will be positive 9 and negative 2. So now I try to factor again, and I see you can't do that with the sum of two squares. It doesn't work. This, if the 2 were a perfect square, we could factor some more. But it's not. So what I have to do is set each of these equal to 0. And then find my solutions. So here I would subtract 9 from both sides. X squared equals negative 9. Take the square root of both sides. And x equals plus or minus 3I. Here I would have to add 2 to both sides. So x squared would equal 2. Take the square root, and x equals plus or minus the square root of 2. And again, we found all 4 of those zeros. It was a 4th degree polynomial, and there should be 4 zeros, and that's what we have up there. Then we go to review problems here. And I'm going to slide this down a little bit since it's switched gears on me. Number 61 says, which value is not a solution of x to the 4th minus 3x squared minus 54 equals 0? Well, if I know the solutions, then I can answer that question. So I take a look at it. There's no common monomial factor. I look for a perfect square trinomial, but negative 54 is not a perfect square. So just like the last problem, I'm trying to figure out two numbers that multiply to negative 54 and add to negative 3, and that will be negative 9 and positive 6. Now this time I can keep going because this is a difference of two squares pattern. So I could go ahead and factor x squared minus 9 to x plus 3 and x minus 3. But x squared plus 6, well, 6 is not a perfect square, and we cannot factor a sum of two squares. So what I have to do is subtract the 6 from both sides, and then take the square root, and x will equal plus or minus, and then we have our negative underneath that radical, so that'll be I square roots of 6. And if we want that in standard form, we would go ahead and write it as plus or minus the square root of 6i. And then I'm just going to finish up these other zeros really quick here. That'd be negative 3 and 3. So that's how you have to go after that one to get all four of them. And then, pardon me, this was multiple choice. So which is not an answer? Right there, negative 3i. Number 62. 62 says Ava drove 3 hours at 45 miles per hour. How many miles did she drive? I hope none of you ever forget that little formula, distance equals rate times time. And that's the reason I had this in the review problems here. The rate is going to be 45 miles per hour, which really would be miles and then per 1 hour down here. So it's kind of like a fraction. And then we have 3 hours that we're going to multiply that by. And this is called dimensional analysis or unit analysis, because what's going to happen here is, because the label of hours is on the top and the bottom, that's going to cancel out. And top times top is going to give us 135 with the only label that's remaining, which is miles, and bottom times bottom would be 1. So it's going to be 135 miles, which would be I. Then, number 63, I gave you one of these earlier this year as a challenge problem, and I hope that you're able to follow along a little better with this one. If not, do it yourself. And that's because we know all of our roots, our zeros, come from the form x minus a. So, pardon me, this will be x minus 1 plus I square roots of 2. And then we'll have x minus 1 minus I square roots of 2. And we have to multiply those together using FOIL so that we can figure out which polynomial had that as a 0. So first times first is just going to give me x squared. Outside, pardon me, times outside will be negative x times 1 minus I square roots of 2. Inside times inside will be negative x times 1 plus I square roots of 2. And then last times last, a negative and a negative will give us a plus. But this is where we have to do the FOIL on those sets of parentheses that we see there. All right. So, might as well just multiply from left to right here and get all of this done, because practically everything's in parentheses. So we'll have x squared, and then negative x times 1 will be negative x. Negative x times negative I square roots of 2 will be plus xi square roots of 2. Then with the next set of distributing, we will get negative x and minus xi square roots of 2. Pardon me. And that is just from going ahead and distributing that negative x. And then the last two, this is the difference of two squares pattern here. So we don't have to do O and I. We can just multiply first times first, which will give us 1, and then last times last, which will be negative I squared square roots of 4. So as we look at this long list of stuff here, we realize that these two are going to cancel each other out, and we're going to have x squared minus 2x plus 1 minus, well then we have an I squared, which is a negative 1, and the square root of 4, which is a 2. So this will be x squared minus 2x plus 1 plus 2, which is x squared minus 2x plus 3. So we go back up, since this was multiple choice, x squared minus 2x plus 3. So that's the polynomial that has those complex roots. And like I said, hopefully you're better able to follow along with this now. This is the second time I've given you a challenge problem like this, and hopefully it's going better. Then number 64. Another really good review problem, kind of an ACT problem here. Sam has only quarters and dimes in his pocket. He has a total of 12 coins, totaling $1.95. So I see two labels here. I've got one about coins, and then I have one about money. So the dimes and the quarters in his pocket are 12. There's 12 coins. But the other one about money, I have to make sure that I put in the values of money that belong with dimes and quarters. And that's going to be 10 cents and 25 cents. So then the next thing I do is I just decide how am I going to solve this one, substitution or elimination. And I like substitution, so I'm going to go ahead and up here at my top, I'm going to subtract d from both sides. So this will be 0.10d plus 0.25, and now I'm going to substitute negative d plus 12 for q, and do the math. So 0.10d minus, because we have a positive 0.25 and a negative d, so minus 0.25d plus, well, 0.25 times 12 is the same thing as dividing it by 4, so that'll be $3.95. Put my two d's together, negative 0.15d, subtract 3 from both sides. So we have, let's see, negative 1.05. And last but not least, we'll go ahead and divide both sides by that negative 0.15. And that will get us the number of dimes for number 64. And that comes out to 7. And since there were 12 total, that means we'll have 5 quarters. So a little bit of work there, but that, again, a great ACT, SAT type of question. Final exam in this class would probably have something like that on it. Then number 66 says write each polynomial in factored form and check by multiplication. So a couple of things I'm thinking about when I go ahead and write down a problem that's this long is, first of all, there's 4 terms. So eventually I'm going to use grouping. But you know what? There's some big numbers here. And all of these numbers that I see here are even. So at the very least, I can pull a 2 out. And every single one of them has an x. So I can also take an x out and then just work backwards. This will need to be x to the 3rd. This will be 3x squared. This will be minus 9x. And then this will be a negative 27. Now, I see I have 4 terms, so what I'm going to do is attempt to factor it by grouping. Remember, we have to trick our brain into seeing something it really does not want to see with the 4 terms. So we notice in the first set of red parentheses here that we can take an x squared out of that, and that will give us x plus 3. And then the second set we can take a negative 9 out of, and that will give us an x plus 3, which is great because that means that x plus 3 was a factor all along, and we just couldn't see it. Pardon me. So we have the 2x and the x plus 3, and then we put the 2 leftovers in the last set of parentheses, and we realize we can still factor this further because that's a difference of 2 squares. And now we notice we could condense this and write that x plus 3 as x plus 3 squared because there were 2 of those. So 2x times x plus 3 squared times x minus 3. Really great method going on there. Then number 70, I might be able to fit that one on here. We have 2x squared minus 5x minus 3 equals 0, and we're supposed to solve by factoring. This does not have a common monomial factor, and it's not a special pattern. And I'm going to have to deal with the fact that there's a 2 in the front by finding the factors, and that would be 1 and 2 and 2 and 1. And then in the back, factors of -3 that could somehow add to -5 in the middle, we're going to have one of those be negative at a time. So it could be -1 and +3, it could be +1 and -3. So now we need to do the outside times outside plus inside times inside to find that -5. And it's right there, because 2 times -3 is -6, and 1 times 1 is 1, and -6 plus 1 is -5. So this is going to be first times first, last times last, and then we just continue on by saying, all right, 2x plus 1 could equal 0, so subtract the 1, divide by 2, and here we get a 0 of 3. So there are the 2 zeros. Then, number 71 and 72. These are kind of monsters. You just have to keep track of where everything is. What we want to do is substitute in. So this will be 16 times 1 minus 4 times -2 minus 2. And that's all over 4 times 1 minus 3 times -2. Now, go ahead and do your parentheses here. And that will give you 16 times -3 times -4. And that's all over 4 times -2 times -2. And at this point, this is all multiplication in the top and the bottom, so we certainly could do some canceling here if we wanted to do the canceling. Or you could just do top times top times top, bottom times bottom times bottom, and then divide. But we have -2 and -2 here. That's going to give us 4. I could cancel that out with that 4. And I'm not worried about the negatives because I had 2 negatives on the top and 2 negatives on the bottom, so the answer is pretty obviously going to be positive. And then I can cancel out a 4 with that 16, and that'll leave me with 4 up top. And I'm just going to go ahead and make sure that I recognize that that 3 is positive. So top times top times top is 12. Bottom times bottom is 1. Because when you're canceling, a 1 takes the position there when you divide those pieces out. So the answer is 12. And I'll leave you to 72 to see what you can do with that one.